The universe began 13.8 billion years ago. That is what they told us. A singular point, infinitely hot, infinitely dense, the beginning of everything. But physicists knew this story had a fatal flaw. The math broke down. The laws of physics collapsed. For decades, we built our understanding of reality on quicksand, and now evidence is emerging that changes the entire picture. Before the hot Big Bang, there was something else, something cold, something vast, something that challenges everything you thought you knew. If you are curious about the cosmos, hit that subscribe button. Prepare yourselves. We begin. In 1927, a Belgian priest named Georges Lemaitre made a discovery that would haunt physics for the next century. He traced the expanding universe backward in time, further and further back, until everything collapsed into a single point, a singularity, zero volume, infinite density, infinite temperature. The math screamed at him. This cannot exist. Albert Einstein hated it. He called it unnatural, but the evidence kept mounting. Edwin Hubble watched galaxies racing apart. The universe was expanding. Run the film in reverse, and you arrive at that impossible moment. Here is the problem they never told you. General relativity, Einstein's masterpiece, completely fails at a singularity. The equations divide by zero. They produce infinity. In physics, infinity means one thing. Your theory is broken. Imagine trying to describe what happens when you divide 1 by a number that keeps getting smaller. 1 divided by 1 is 1. 1 divided by 0.1 is 10. 1 divided by 0.01 is 100. As the denominator approaches 0, the answer shoots toward infinity. At exactly 0, mathematics collapses. This is what happens at the Big Bang singularity. For decades, cosmologists taught this story anyway. The Big Bang happened 13.8 billion years ago. Space, time, matter, and energy burst into existence from nothing. But they knew, in quiet conference rooms and late-night discussions, that this explanation was incomplete. Stephen Hawking proved it mathematically in 1970. Working with Roger Penrose, he showed that if general relativity is correct, then the singularity is unavoidable. The universe must have begun in this impossible state. Their theorem was elegant and devastating. It meant that the most successful theory of gravity in history could not explain the origin of the universe. Think about that. The theory that describes black holes, GPS satellites, and the bending of starlight fails completely at the one moment that matters most. The beginning, scientists tried to ignore this. They focused on what happened after the first tiny fraction of a second, the formation of atoms, the birth of stars, the evolution of galaxies. All of that physics works beautifully, but the initial moment remained a forbidden zone, a place where the laws break down. The singularity problem is not just mathematical, it is philosophical. If the laws of physics did not exist at the beginning, then how did the universe begin? What caused space and time to suddenly exist? Why is there something rather than nothing? For years, physicists assured the public that the Big Bang was the ultimate answer, but among themselves, they whispered a different truth. The singularity is a sign that we are missing something fundamental, some deeper theory, some hidden layer of reality. They were right to whisper, because new evidence is now revealing what they suspected all along. The Big Bang was not the beginning, it was a transition, and what came before it is stranger than anyone imagined. In 1981, a young physicist at MIT had a radical idea that would change cosmology forever. Alan Guth proposed that the universe underwent a period of explosive growth before the hot Big Bang. He called it cosmic inflation. Within a fraction of a second, space doubled in size, then doubled again and again, at least 80 times in total. This solves a mystery. The cosmic microwave background, the afterglow of the Big Bang, has almost exactly the same temperature everywhere we look, about 2.7 degrees above absolute zero. But how could regions of space, billions of light years apart, have the same temperature if they never had time to exchange energy? Inflation provides the answer. Before the explosive expansion, these regions were close together, close enough to reach thermal equilibrium. Then inflation stretched them apart, faster than light could travel between them. The uniform temperature is not a coincidence. It is a frozen memory of a time before the expansion. But here is what they did not emphasize. If inflation happened before the hot Big Bang, then the Big Bang was not the beginning. Something existed before it. An inflationary phase that lasted for an unknown amount of time, maybe a fraction of a second, maybe billions of years. We do not know. The inflationary universe was not hot and dense. It was cold and empty, nearly at absolute zero. The vacuum of space itself carried a strange form of energy that pushed the universe apart. This energy did not dilute as space expanded. Instead, it remained constant, driving faster and faster growth. Picture a sheet of rubber being stretched in all directions at once. Any wrinkles or bumps get smoothed out. Any curvature becomes flat. This is what inflation did to space itself. It took whatever messy, chaotic state existed earlier and flattened it into a uniform canvas. Then, something happened. The inflationary energy transformed. It decayed into particles and radiation, flooding space with intense heat. This transition is what we call the hot Big Bang. The universe went from cold and empty to hot and dense in an instant. But it was not a beginning from nothing. It was a phase transition. Think of water freezing into ice. The ice does not appear from nothing. It forms when liquid water changes state. The hot Big Bang was similar. It emerged when the inflationary vacuum changed state, releasing its stored energy. This theory is confirmed, not by philosophy or wishful thinking, but by hard evidence. The pattern of galaxies we see today matches the predictions of inflation perfectly. The slight variations in temperature across the cosmic microwave background fit the model exactly. The flatness of space, the distribution of matter, the absence of exotic defects like magnetic monopoles, all of it points to inflation. What does this mean? It means the universe existed before the event we call the Big Bang, in a different state with different physics. And that raises an even bigger question. If inflation created the conditions for the hot Big Bang, what created inflation? Where did that cold, empty, expanding space come from? The answer takes us beyond the standard model of cosmology, into territory that most scientists avoided discussing for decades. In 2003, scientists made a discovery that would confirm inflation and prove something existed before the Big Bang. They analyzed data from the Wilkinson Microwave Anisotropy Probe, a satellite mapping the oldest light in the universe. What they found was hiding in plain sight for decades. The cosmic microwave background contains patterns, tiny temperature fluctuations across the sky. Some of these patterns are on scales smaller than the distance light could have traveled since the Big Bang. These are called sub-horizon fluctuations. They make sense in any cosmological model, but other patterns are different. They exist on scales larger than our cosmic horizon, bigger than any region that could have been in contact after the Big Bang. These superhorizon fluctuations should not exist unless something happened before. Imagine two people on opposite sides of Earth trying to coordinate without any communication. They cannot do it. They have no way to know what the other is doing. Similarly, regions of space beyond each other's horizons cannot coordinate their properties, yet somehow they did. The graph that changed everything showed correlations between temperature and polarization in the cosmic microwave background. On small scales, the data bounced up and down as expected, but on large scales, there was a clear dip, a signature that matched inflation perfectly and contradicted the old singular Big Bang model. This is not subtle. The difference between the two predictions is stark. A universe that began with a singularity would show no correlations on superhorizon scales. The data would be flat, random. But a universe that went through inflation before the hot Big Bang would show exactly what we observe. A a specific pattern of correlations that reflects the pre-Big Bang state. The Planck satellite, launched years later, confirmed these findings with even greater precision. It mapped the cosmic microwave background in exquisite detail. Every new measurement strengthened the case for inflation. The superhorizon fluctuations are real. They are robust. They are undeniable. Here is what this means in plain language. Information from before the hot Big Bang survived and left imprints on the universe we see today. The fluctuations that eventually became galaxies and stars originated during inflation. They were quantum ripples in space, stretched to cosmic scales by the exponential expansion. These ripples froze in place, creating the seeds of all structure. When the inflationary energy decayed and the hot Big Bang began, those frozen patterns remained. They heated up, they evolved, but they never forgot their origin. The universe today is a direct descendant of the pre-Big Bang state. This evidence is strong enough that it earned comparisons to a Nobel Prize. It is one of the most important confirmations in modern cosmology. Yet, most people never heard about it. The media reported that we mapped the baby universe. They showed colorful pictures of temperature variations. But they missed the deeper story. We detected something from before the Big Bang, a whisper from an earlier epoch carried forward through the transition. The hot Big Bang did not erase the past, it transformed it, and that transformation left fingerprints. What does this tell us about the nature of reality? It tells us that the universe has a history stretching back beyond the moment we once called the beginning. And if we can detect traces of that earlier epoch, maybe we can figure out what it was like. But what comes next is even stranger. The inflationary epoch redefined our understanding of the cosmos. Before 1981, we thought the universe began hot and dense. We were wrong. The evidence now confirms that before the heat, there was cold. Before the density, there was emptiness. The pre-Big Bang universe looked nothing like what came after. Picture space almost at absolute zero, empty, silent, dark. Not the darkness of night, but the absence of everything. No stars, no atoms, no particles. Just the fabric of space itself, carrying a mysterious energy that caused it to expand. This energy is called the inflaton field. It permeated every point in space. Unlike normal matter or radiation, it did not dilute as the universe grew. Instead, it maintained constant density. As space doubled in size, the total energy doubled too. This seems impossible, but it is what the equations demand. Where did this energy come from? That question leads us into deep waters. In quantum physics, empty space is never truly empty. The vacuum seethes with fluctuations. Virtual particles pop in and out of existence. Fields oscillate. This activity has energy. During inflation, that vacuum energy dominated everything. Think of it like a compressed spring. The vacuum was in a high energy state, and it wanted to roll down to a lower energy state. But the transition took time. During that time, the energy stored in the vacuum drove the expansion. Space grew exponentially, doubling every tiny fraction of a second. 80 doublings sounds modest until you do the math. Start with a region the size of a grapefruit. After 80 doublings, it becomes larger than the observable universe, vastly larger. The expansion was so extreme that it took whatever existed before and stretched it beyond our ability to ever observe. This has profound implications. If the universe before inflation had structure, complexity, or patterns, inflation erased almost all of it. It smoothed everything out. The only things that survived were quantum fluctuations, which got amplified into the patterns we see today. Scientists calculate that inflation lasted at least long enough for 80 doublings. But it could have lasted longer, much longer. There is no upper limit. The inflationary epoch might have continued for billions of years before ending, or it might have lasted only a fraction of a second. We cannot tell. What ended inflation? At some point, the inflaton field decayed. It transitioned to a lower energy state. like a ball rolling down a hill. When it reached the bottom, all that stored energy had to go somewhere. It converted into particles and radiation. This conversion heated up space to incredibly high temperatures. This is the hot Big Bang. Imagine a frozen lake suddenly melting and catching fire at the same time. That is roughly what happened during the transition from inflation to the hot Big Bang. The cold, empty vacuum transformed into a searing plasma of quarks, electrons, and photons. The universe went from serene to violent in an instant. But here is the key insight. The hot Big Bang was not a beginning. It was an awakening. The universe already existed during inflation. It was just in a dormant state. The transition brought it to life, allowing particles to form, forces to operate, and evolution to begin. This reframes the central question of cosmology. We no longer ask what caused the Big Bang. We ask what caused inflation. What set up that cold, empty, expanding space? What came before the inflationary epoch? And that question leads us to even more exotic theories. To understand how extreme inflation was, we need to think about exponential growth. This is not linear expansion, where you add the same amount each time. This is doubling. Each step multiplies what came before. Start with 1 penny, double it, 2 pennies, double again, 4, then 8, then 16. This seems harmless at first, but keep going. By the 28th doubling, you have over $2 million. By the 38th doubling, you have over $200 billion. By the 64th doubling, you have more wealth than exists on Earth. The universe underwent at least 80 doublings during inflation. 80. Every doubling happened in an incomprehensibly short time. The entire process took less than a second, perhaps much less. We are talking about timescales where our intuition completely fails. Here is another way to picture it. Take a balloon, blow it up so it doubles in size. Now imagine the material of the balloon doubles again and again. After 10 doublings, a balloon the size of your fist becomes larger than a house. After 20 doublings, larger than Earth. After 40 doublings, it exceeds the solar system. After 80 doublings, it dwarfs the observable universe by an unimaginable factor. This is what happened to space itself. Not an explosion pushing matter outward through existing space, but the actual fabric of space expanding. Coordinates that were close together got stretched light years apart, then millions of light years, then billions, all while inflation continued. The quantum fluctuations present in the tiny pre-inflationary patch got stretched along with space. These fluctuations were originally smaller than an atom. After inflation, they were larger than galaxies. This amplification process is why we see structure in the universe today. Inflation took microscopic quantum randomness and turned it into cosmic architecture. But there is something unsettling about this picture. If inflation expanded space by such an enormous factor, then the observable universe we see today is just a tiny fraction of what exists. The full universe is vastly larger, so large that light from most of it will never reach us. We are living inside one small bubble, ignorant of the greater reality beyond. Some scientists argue that inflation never completely stopped. In most regions, it continues. Our observable universe occupies a spot where inflation ended 13.8 billion years ago. But elsewhere, space is still doubling, creating new regions, new bubble universes, each one isolated from the others. This is called eternal inflation. It suggests that the process which created our universe is ongoing. New universes constantly bubble into existence from the inflating background, each one potentially with different properties, different laws of physics, different constants of nature. We inhabit just one among infinite possibilities. Think about what this means for the question of beginnings. If inflation is eternal, then our Big Bang was not even the first. It was one event among countless others, scattered across an infinitely large and eternally inflating multiverse. The hot Big Bang marked the beginning of our local region, but not the beginning of reality itself. This makes the question even more urgent. If eternal inflation is correct, where did it start? Did it have a beginning, or has it always existed? Can we even talk about a first moment if time itself emerged from the inflationary process? These are not just philosophical puzzles. They are scientific questions with testable implications. The pattern of fluctuations in the cosmic microwave background carries information about the inflationary process. Future observations might reveal whether eternal inflation is real, whether our universe is alone or one of many. For now, we know this much. The doubling universe is real. The evidence confirms it, and it pushes the question of ultimate origins back beyond the hot Big Bang into territory we are only beginning to explore. This is the trillion-dollar question. Inflation requires energy, enormous amounts of it, enough to stretch a microscopic region into something larger than the observable universe. Where did that energy come from? The answer challenges our basic intuitions about physics. In everyday life, energy is conserved. You cannot create it or destroy it. You can only transform it. Burn gasoline, and chemical energy becomes heat and motion. Drop a ball, and potential energy becomes kinetic energy. The total remains constant. This principle is one of the most fundamental laws in physics, but general relativity changes the rules. When space itself expands, energy conservation becomes subtle. The energy in the universe can increase because space carries energy. During inflation, as space doubled in size, the total vacuum energy doubled too. The universe essentially created energy out of nothing. This sounds like magic, but it is allowed by the equations. The key is that gravity has negative energy. As space expands and creates more vacuum energy, the gravitational field becomes more negative. The two effects balance. The total energy of the universe remains zero. You can create infinite amounts of vacuum energy as long as you create equal amounts of negative gravitational energy. Think of it like a credit card. You can charge as much as you want, but your debt increases by the same amount. Inflation ran up an enormous energy bill, but gravity paid for it with negative debt. The ledger balanced. This is confirmed not just by theory, but by measurement. The observable universe has almost exactly flat geometry. This means the total energy, including the negative gravitational energy, is very close to zero. We live in a universe that costs nothing, but this raises another question. What started the inflaton field in the first place? Where did the vacuum energy that drove inflation come from originally? Here the answers become more speculative. Some physicists propose that quantum fluctuations in a pre-existing space triggered inflation. Others suggest that inflation has no beginning, that it is eternal to the past. One intriguing idea is that inflation started from quantum uncertainty itself. In quantum mechanics, fields can tunnel through energy barriers. Maybe the vacuum of space tunneled from a lower energy state to a higher one, initiating inflation. This is called quantum tunneling from nothing. The word nothing here is misleading. It does not mean absolute nothingness. It means the lowest possible energy state allowed by quantum physics. Even that state has properties. It has geometry. It has quantum fluctuations. It is something, not nothing. Physicist Alexander Vilenkin developed a mathematical description of this process. He showed that under certain conditions, a universe can quantum tunnel into existence from a state that approximates nothing. The probability is incredibly low, but in an infinite multiverse, low probability events happen. Other physicists remain skeptical. They argue that quantum tunneling requires time to occur, but time itself emerged during inflation. How can something happen before time exists? This is where the physics becomes truly mind-bending. We are asking questions at the boundary of what science can currently address. What we know for certain is that inflation drew its energy from the vacuum of space. That vacuum energy converted into particles and radiation during the hot Big Bang. The energy that powers the sun, that lights up galaxies, that allows life to exist, all of it came from the decay of the inflaton field. In a very real sense, we are made from the energy of empty space. The atoms in your body trace their origin back to that moment of transition. When inflation ended and the hot Big Bang began, vacuum energy transformed into matter. That matter evolved into stars, planets, and eventually us. But if vacuum energy could power inflation, what else might it do? This question leads us to one of the most bizarre proposals in modern cosmology. In 1983, Stephen Hawking proposed an idea so radical that it redefined the concept of time itself. He suggested that the universe has no beginning, not because it is eternal, but because the question of a beginning becomes meaningless. Time itself bends in a way that eliminates the boundary. The proposal uses a concept from quantum physics called imaginary time. In normal time, events happen in sequence. Past leads to present, leads to future. But in imaginary time, this sequence dissolves. Time becomes more like space. You can move in any direction. There is no special starting point. Hawking suggested that near the moment of the Big Bang, time transitions from imaginary to real. As you go back further and further, time becomes more and more space-like. Eventually, the distinction between time and space disappears completely. The universe has no edge, no beginning, no moment when things started. Think of Earth's surface. You can walk north and north and north. Eventually, you reach the North Pole. But then what? There is no point farther north. The North Pole is not a boundary. It is simply the limit of the coordinate system. Asking what lies north of the North Pole is meaningless. Hawking suggests the beginning of time is similar. This proposal elegantly sidesteps the singularity problem. If time smoothly transitions to a space-like dimension, then there is no moment of infinite density, no breakdown of physics. No need to explain what caused the Big Bang. The universe simply exists as a four-dimensional shape with no boundaries in space or time. But does this match reality? The honest answer is we do not know. Hawking's proposal is mathematically beautiful. It solves several conceptual problems, but it makes few testable predictions. We have no way to observe imaginary time. We cannot measure the transition Hawking describes. The proposal remains speculation. Some physicists embrace it. They argue that it provides the most elegant solution to the beginning problem. Others reject it. They claim that imaginary time is just a mathematical tool, not a physical reality. The debate continues. What we can say is that Hawking identified a deep issue. Our concepts of time and causality break down near the Big Bang. We talk about what happened before, but maybe before has no meaning in that regime. Maybe the universe does not have a temporal origin because time itself emerged gradually. This connects to a broader theme. All of these theories, inflation, Hawking's boundary proposal, the ideas we will explore next, they all suggest that the Big Bang was not a true beginning. It was a transition, a phase change, an emergence of the universe we know from something stranger and less familiar. Hawking worked with Jim Hartle on this idea, developing it into a full mathematical framework. They called it the no-boundary proposal. The universe, they claimed, is finite in time but has no starting point, just as a sphere is finite in size but has no edge. Critics point out that this does not really answer the question. It just reframes it. Instead of asking why the universe began, we ask why the universe has the particular no-boundary shape it does. Why not some other shape? Why this set of laws? The mystery remains. Yet, the proposal has value. It shows that our intuitive concepts fail at extreme scales. We think of time as something absolute, flowing from past to future. But general relativity taught us that time is flexible. It bends, it stretches, it slows down near massive objects. Hawking pushed this further, suggesting that time can transform into something else entirely. If he is right, then the question what came before the Big Bang is ill-posed. Not because the answer is forbidden knowledge, but because the question assumes a linear time that did not exist. Still, most physicists think there is more to the story. and some of them have developed theories that make very different claims. Roger Penrose, the Nobel Prize-winning physicist who proved singularities exist in black holes, proposed a cosmology that turns everything upside down. He claims the Big Bang was not the beginning. It was the end of a previous universe, and that previous universe was itself the end of an earlier one. The cycle continues forever. Infinitely many universes, each emerging from the death of the last. He calls this conformal cyclic cosmology. The name comes from the mathematical technique he uses to connect the end of one universe to the beginning of the next. But the idea is more intuitive than it sounds. Picture the far future of our universe. Trillions of years from now, all the stars have died. All the matter has been swallowed by black holes or dispersed into the void. Even the black holes evaporate away through Hawking radiation. What remains is nothing but empty space, filled with photons traveling through the darkness. In this state, nothing has mass. No particles, no atoms. Everything has decayed or been converted to light. And here is where Penrose makes his move. If nothing has mass, then nothing has a natural scale of size. A universe with no massive particles looks the same whether it is huge or tiny. Time and distance lose meaning. Penrose suggests that this final state of our universe can be mathematically transformed to look like the initial state of a new universe. The infinite future of one cycle becomes the Big Bang of the next. The universe does not end in a big crunch, crushing everything into a singularity. Instead, it smoothly transitions into a new beginning. This solves one of cosmology's biggest puzzles. The early universe had extremely low entropy. It was highly ordered, uniform, smooth. Why? In most theories, this low entropy beginning is just assumed. It is a mystery. But Penrose argues that the late universe naturally becomes smooth again after everything decays. The low entropy at each Big Bang is inherited from the high entropy end of the previous cycle. If this theory is correct, then our Big Bang contains remnants of the previous universe. Signals from that earlier epoch should appear in the cosmic microwave background. Penrose claims he has found them. He points to anomalous patterns, concentric circles of temperature variation, spots that are hotter than they should be. He interprets these as Hawking points, the final radiation from supermassive black holes in the previous universe, concentrated into bright spots by the transition between cycles. If confirmed, they would prove that something existed before our Big Bang. But here is the problem. Most cosmologists do not believe him. Multiple independent teams have analyzed the same data Penrose uses. They find that the patterns he identifies are not statistically significant. They are the kind of random alignments you would expect by chance, not a signal from a previous universe. This is harsh but important. Penrose is a brilliant physicist. His work on black holes is foundational, but that does not mean every idea he has is correct. The evidence for conformal cyclic cosmology is weak. The theory makes specific predictions, and those predictions have not been confirmed. In fact, the data supports the opposite conclusion. The superhorizon fluctuations in the cosmic microwave background match inflation perfectly. They do not match what Penrose's theory predicts. If his cyclic cosmology were correct, we should see a different pattern. We do not. Science is brutal this way. You can be a Nobel laureate, beloved by millions, a giant in your field. But if your predictions do not match observations, the theory fails. No amount of reputation or authority overrides data. Still, Penrose's idea is conceptually intriguing. It offers a vision of an eternal cosmos, cycling through phases of birth, evolution, and dissolution. It connects the far future to the deep past in a profound way, and it highlights a real mystery. Why was the early universe so ordered? Why such low entropy? Even if conformal cyclic cosmology is wrong, the question it asks remains valid, and other theories attempt to answer it in different ways. Black holes might hold secrets from before the Big Bang. This is the strange claim at the heart of Penrose's theory. He proposes that in the final moments of a previous universe, supermassive black holes evaporated through Hawking radiation. This radiation was weak at the time, barely noticeable. But during the transition to the next cycle, it got compressed into concentrated spots of energy. These are the Hawking points. Let us understand what Hawking radiation is. Black holes are not perfectly black. They emit particles due to quantum effects near their event horizon. This emission is incredibly slow. A black hole with the mass of the Sun would take longer than the current age of the universe to evaporate. But given enough time, trillions upon trillions of years, even the largest black holes disappear. As a black hole shrinks, it radiates faster. The final moments are explosive. All the remaining mass converts to energy in a brilliant flash. If this happened at the end of a previous universe, that flash would carry forward into the next cycle. Penrose calculates that such events would leave circular marks in the cosmic microwave background. He and his collaborators published papers claiming they found these marks. They identified regions in maps from the Planck satellite that showed excess temperature variation, circles about 5 times the size of the Moon, scattered across the sky. They ran simulations and argued these patterns were too strong to be random. The scientific community responded quickly. Multiple teams reanalyzed the data. They used more rigorous statistical methods. They simulated random cosmic microwave backgrounds to see how often circular patterns appear by chance. The answer was disappointing for Penrose. Such patterns appear frequently. They are not anomalous. They are what you expect from random noise. One team explicitly showed that once you account for the look elsewhere effect, which means considering how many places you looked for patterns, the Hawking points disappear. If you search the entire sky for circles, you will find some. That does not mean they are meaningful. It means you looked in enough places that random chance gave you what you wanted. This is a cautionary tale about data analysis. The cosmic microwave background is incredibly complex. It contains thousands of data points. If you stare at it long enough, you can find patterns. Some will look significant, but statistical rigor demands we account for how many patterns we searched for. Most of what looks meaningful is not. Does this mean black holes from a previous universe could not exist? Not exactly. It means we have no evidence for them. The idea is not ruled out by logic. It is ruled out by observation. If Penrose's theory were correct, the signal should be strong and unmistakable. It is not. Other scientists have proposed different ways a previous universe could leave traces. Some suggest gravitational waves from colliding black holes might propagate through the transition. Others propose that the rotation of galaxies could carry memory of earlier epochs. None of these ideas have gained strong observational support. The problem is fundamental. Any signal from before the Big Bang would have to pass through an incredibly violent transition. The conversion from the cold inflationary vacuum to the hot Big Bang plasma. That transition likely destroys most information. The universe suffers from cosmic forgetfulness. Still, the search continues. New telescopes are planned. More sensitive detectors are being built. If any trace of a pre-Big Bang universe exists in our data, future instruments might find it. For now, the evidence points strongly toward inflation as the pre-Big Bang state, not a previous cycle of matter and radiation. What we can say is this: black holes are gravitational powerhouses. They warp space and time in extreme ways. If anything could carry information through a cosmological transition, black holes are the best candidates. But wanting them to be time capsules does not make it so. The next theories we explore take a completely different approach. They suggest that our universe exists in extra dimensions we cannot perceive, and that the Big Bang resulted from an event in that higher dimensional space. Conformal cyclic cosmology faces a bigger problem than missing Hawking points. It does not explain what it sets out to explain. This is the verdict from most cosmologists who have studied Penrose's proposal in detail. The theory trades one mystery for another without making progress. Remember, the goal is to explain why the early universe had low entropy. why it was so smooth and uniform. Penrose argues that the end of the previous universe naturally becomes smooth again, so the low entropy carries forward. But there is a fatal flaw. Entropy always increases. That is the second law of thermodynamics. Each cycle should have higher entropy than the last. The universe should become more disordered, not less. Penrose tries to sidestep this by claiming that information gets lost when black holes evaporate. That resets the entropy. But this creates its own problems. If information is destroyed, quantum mechanics is violated. Most physicists think information must be conserved. Even in extreme gravitational environments, there is another issue. The theory requires all particles with mass to eventually decay. Protons must fall apart. Electrons must lose their charge or mass. Otherwise, the conformal rescaling does not work. Massive particles have a characteristic size, their Compton wavelength, which sets a scale. That scale breaks the conformal symmetry. Proton decay is not impossible. Some theories beyond the standard model predict it, but we have never observed it. Experiments have set very tight limits. Protons must live longer than 10 to the 34 years if they decay at all. And electrons are believed to be perfectly stable. They are the lightest charged particle. They have nothing to decay into. Penrose acknowledges these problems. In later presentations, he softened the requirements. He suggested that maybe some mass can remain as long as it is insignificant, but this makes the theory less predictive. It adds flexibility, which in physics is often code for adding adjustable parameters to fit the data. The deeper critique is more philosophical. Even if cyclic cosmology worked perfectly, it would not answer the ultimate question. It would just move it back infinitely. Instead of asking why this universe began, we ask why the infinite cycle exists, why these laws, why this pattern. The explanation becomes circular. Inflation does not suffer from this problem. It explains the smoothness and flatness of the universe without requiring previous cycles. It makes specific predictions about the pattern of fluctuations, and those predictions match observations. It connects to particle physics in concrete ways. The inflaton field could be a real quantum field, not just a mathematical construction. Most importantly, inflation is testable. It predicts a background of primordial gravitational waves. These waves would leave a distinct signature in the polarization of the cosmic microwave background. Experiments are searching for this signature right now. If found, it would confirm inflation beyond any doubt. If not found, inflation might need revision. Cyclic cosmology makes fewer concrete predictions. The ones it does make have not been confirmed. This is why the community has largely moved on. Not because Penrose is not brilliant, not because the questions are not worth asking, but because the theory does not match reality. Science is pragmatic. We use theories that work, that make accurate predictions, that open new avenues for understanding. Inflation does this. It has become the standard model of the early universe because it earns that position through evidence. Does this mean cyclic cosmology is completely wrong? Maybe not. Perhaps some version of it, modified and refined, could work, but that version would need to address the problems we have outlined. It would need to make testable predictions, and it would need to match the data better than inflation. For now, when cosmologists discuss what came before the Big Bang, they talk about inflation, not cycles, not previous universes of matter and stars, but a cold, empty, exponentially expanding vacuum. That is where the evidence points. Yet, there are other ideas that do not rely on cycles or Hawking points, ideas rooted in string theory and the mathematics of extra dimensions. Reality might have more dimensions than the 3 of space and 1 of time we experience. This is not science fiction. It is a serious possibility from string theory, one of the leading frameworks for unifying quantum mechanics and gravity, and these extra dimensions could hold the key to what came before the Big Bang. String theory proposes that the fundamental building blocks of reality are not point particles, but tiny, vibrating strings. These strings are unimaginably small, about 10 to the negative 35 meters. That is 20 orders of magnitude smaller than an atomic nucleus. At that scale, new physics emerges. Space itself has structure, but the theory only works if space has 10 dimensions, not 4, 10. 3 that we see, plus 1 of time, plus 6 more that we cannot perceive. Where are these extra dimensions? The standard answer is that they are curled up, rolled into tiny shapes so small that we cannot detect them. Picture a garden hose. From far away, it looks one-dimensional, a line. But zoom in, and you see it has thickness. It is actually two-dimensional, a surface wrapped into a cylinder. The extra dimension is hidden by scale. String theory suggests something similar. What we perceive as three-dimensional space might actually be nine-dimensional, with 6 dimensions curled up at every point. The shape of these curled dimensions matters. It determines what kinds of particles and forces exist. Different shapes produce different physics. Some shapes allow electrons and quarks, others do not. The landscape of possible shapes is vast, perhaps 10 to the 500 different possibilities. Each one corresponds to a different universe with different laws. This connects to the question of the Big Bang in a surprising way. Maybe our three-dimensional universe exists on a structure called a brane, short for membrane. This brane floats in a higher dimensional space called the bulk. We are stuck on the brane. We cannot move into the bulk, but gravity can. Gravity must exist in all dimensions because it is the curvature of space itself. This idea, proposed by physicists Lisa Randall and Raman Sundram, explains a long-standing puzzle. Why is gravity so much weaker than the other forces? An electron and a proton attract electromagnetically with a force that is 10 to the 39 times stronger than their gravitational attraction. This is the hierarchy problem. If gravity spreads through extra dimensions while other forces are confined to our brane, it would dilute gravity's strength. The force gets weaker because it has more space to spread through. Meanwhile, electromagnetism and the other forces remain strong because they are concentrated on our brane. But what does this have to do with the Big Bang? If our universe is a brane in a higher dimensional space, then the Big Bang might not have been the beginning of that space, only the beginning of our brane. Something could have existed in the bulk before our brane formed. Other branes, other universes, a pre-existing higher dimensional reality. Think of it like being a character in a video game. To you, the game world is all that exists, but the player and the computer running the game exist outside that world. They are in a higher dimension that you cannot perceive or access. Similarly, we might be confined to a three-dimensional brane, unaware of the larger reality around us. This is speculative. No experiment has detected extra dimensions. Particle accelerators have looked. They smashed protons together at enormous energies, searching for signs that energy disappears into unseen dimensions. They found nothing. If extra dimensions exist, they are either too small or too weakly interacting to detect with current technology. But the mathematics is compelling. String theory has survived decades of scrutiny. It makes finite predictions where other theories give infinity. It unifies forces in elegant ways. It might be the long-sought theory of quantum gravity. And if it is right, then extra dimensions exist, which means the Big Bang story is more complex than we thought. What comes next is even more startling. If our universe is a three-dimensional brane floating in higher dimensional space, then we need to ask the next question. Are there other branes? Could other universes exist alongside ours, separated by a microscopic distance we cannot perceive? The answer might be yes. In the brane scenario, the bulk can contain multiple branes. Each one is a separate universe with its own space, time, and matter. We cannot see these other universes because light is trapped on our brane. Photons cannot jump across the bulk. They travel only on the surface where we live. But gravity is different. The graviton, the particle that carries gravitational force, is not confined to any brane. It exists in the full geometry of the bulk. This means gravity can travel between branes. Gravitational interactions could link separate universes, even though nothing else passes between them. Picture parallel sheets of paper floating in a room. Each sheet represents a universe. Creatures living on one sheet cannot see creatures on another sheet. Their light travels only on their surface. But if the sheets warp and bend, they can feel each other's presence through gravity. The geometry of one affects the other. This setup creates fascinating possibilities. Maybe the strength of gravity we measure depends on how far we are from other branes. Maybe dark matter is ordinary matter on a nearby brane, pulling on us gravitationally but invisible because its light cannot reach us. These ideas are not mainstream, but they illustrate the range of possibilities. The bulk itself might have its own physics. It could contain fields, particles, even structures we cannot imagine. Our brain would be embedded in this larger reality, like a photograph in an album. We see only our page, but the album contains many pages. The Big Bang would not mark the beginning of the album, only the beginning of our page. In some versions of Brane cosmology, the branes move through the bulk. They can approach each other. They can collide. And when they collide, the energy released is enormous. This is the ekpyrotic scenario, proposed by physicists including Paul Steinhardt and Neil Turok. Picture two branes moving toward each other through the bulk. As they get closer, their gravitational attraction increases. Tiny wrinkles form on their surfaces. These wrinkles are quantum fluctuations. When the branes finally collide, the kinetic energy of the impact converts into particles and radiation. This collision is the Big Bang. In this model, our universe did not emerge from nothing. It emerged from the collision of pre-existing branes. The cold, empty space before the collision is what we call the inflationary epoch. The hot, dense state after the collision is the hot Big Bang. The transition is violent but finite. No singularity, no breakdown of physics. After the collision, the branes bounce apart. They separate, expand, and eventually cool. Then they start approaching again. The cycle repeats. Each collision creates a new, hot Big Bang. Each separation creates a new inflationary phase. The universe oscillates between these states forever. This is elegant in some ways. It provides a concrete mechanism for the Big Bang. It explains why the universe began in a low entropy state. The collision smooths out irregularities. It also connects cosmology to string theory in a natural way. The branes are not ad hoc additions. They emerge from the mathematics of extra dimensions. But the theory has problems. The main one is the transition. How do you go from the collision, where energies are extreme and space is chaotic, to the smooth, hot Big Bang we observe? The math is hard. Some calculations suggest the transition is unstable. It does not produce the uniform universe we see. Instead, it creates a mess. Physicists have worked on this problem for years. They have refined the models, added new fields, adjusted parameters. Some versions work better than others, but none is fully satisfactory. The ekpyrotic scenario remains a promising idea without definitive proof. What would prove it? The pattern of primordial gravitational waves. Inflation and ekpyrotic cosmology make different predictions about these waves. Inflation predicts a strong signal. Ekpyrotic models typically predict a weak signal, possibly undetectable. Future experiments measuring the cosmic microwave background polarization will test this. For now, branes remain theoretical, beautiful mathematics, but we have no direct evidence they exist. The word ekpyrotic comes from ancient Greek philosophy. It means conflagration, a universe-destroying fire. The philosophers believed the cosmos periodically burns and is reborn from the ashes. Modern physicists borrowed the term for their brane collision model. The name fits. The collision is violent beyond imagination. Two branes approach each other through the bulk. They are nearly flat, nearly empty, just the vacuum of space on each surface. As they get closer, gravitational effects become important. The attraction between them grows. Any tiny wrinkle on either surface gets amplified. These are the seeds of cosmic structure. The collision itself lasts an infinitesimal amount of time. The branes stick together. All the kinetic energy of their motion converts into heat. The temperature spikes to values that would vaporize any normal matter. But there is no normal matter yet. Only energy, pure energy flooding the branes. This energy condenses into particles, quarks, leptons, photons. The zoo of fundamental particles emerges. They fill space uniformly because the collision happened everywhere simultaneously. There are no special locations, no center, no edge, just a homogeneous sea of particles at incredible temperature. This is the hot Big Bang. Not a singularity, not a beginning from nothing, but a transition from one state to another, from cold and empty to hot and dense. The universe already existed. The collision changed its form. After the collision, the branes bounce apart. They separate. Space expands. The particles cool. Protons and electrons combine to form atoms. Gravity pulls atoms into clumps. Those clumps become stars and galaxies. Everything we see around us originated in that collision and subsequent expansion. But here is where it gets interesting. The branes do not separate forever. They slow down, stop, then start approaching again. Gravity pulls them back together. The cycle repeats. Another collision, another Big Bang, another universe of stars and galaxies, an eternal rhythm of creation and destruction. This model solves several problems. It explains why the universe is so uniform. The collision acts like a reset button. It wipes out complex structure and starts fresh. It explains why the universe is flat. Flatness is the energetically preferred geometry for the branes. It explains why we do not see magnetic monopoles or other exotic defects. They are not produced at the relatively low temperature of the collision. It also makes the Big Bang less mysterious. In the standard model, the universe explodes from a singularity for no apparent reason. In the ekpyrotic model, the Big Bang is caused by a collision. Collisions are something we understand. They happen in particle accelerators. They happen in asteroid impacts. They are part of normal physics, just scaled up to cosmic proportions. Yet, the model has weaknesses. The biggest is making the transition smooth. When two branes collide, the equations predict instabilities, regions where the energy density varies wildly. These should produce an inhomogeneous universe, not the uniform one we observe. Physicists have proposed additional fields to smooth things out, but this adds complexity. Another issue is entropy. Each cycle should increase the total entropy. After many cycles, the universe should be disordered and chaotic, but we see a highly ordered early universe. How does the collision reset entropy? This is not fully solved. Some versions of the theory claim information is lost during the collision. Others invoke quantum effects. None is completely convincing. There is also the question of time. If the cycles are eternal to the past, when did they start? Or did they always exist? If they always existed, why does the universe have the structure it does, rather than some other structure? These questions echo the same problems that plague other cyclic models. Despite these challenges, the ekpyrotic scenario remains active research. It represents a serious alternative to inflation, a different way to think about the early universe, and it is grounded in string theory, which gives it a theoretical foundation that many other speculative ideas lack. Whether it is correct will be determined by observation. The smoking gun would be a specific pattern in primordial gravitational waves, a pattern distinct from what inflation predicts. That pattern would tell us that the Big Bang was not the beginning, but a collision. There is another approach entirely, one that does not require extra dimensions or exotic branes. It goes back to basics, quantum mechanics, and general relativity. These two pillars of modern physics do not fit together. Loop quantum gravity attempts to marry them by quantizing space itself. In classical physics, space is continuous. You can divide it infinitely. Between any 2 points, there is always a point in between. Space is a smooth fabric. But loop quantum gravity says this is wrong. At the smallest scales, space is grainy, made of discrete chunks, atoms of space. These atoms are unimaginably tiny, about 10 to the negative 35 meters across. That is the Planck length. Below this scale, the concepts of distance and geometry break down. You cannot measure anything smaller because space itself comes in minimum units. This is like trying to measure a fraction of a pixel on a screen. At some point, there is no smaller unit. Why does this matter for the Big Bang? Because singularities require infinitely small regions. Zero volume, infinite density. But if space has a minimum size, it cannot shrink to zero. Loop quantum gravity predicts that as you go back toward the Big Bang, density increases, but it hits a maximum. Then something strange happens. Gravity reverses. In normal gravity, mass attracts mass, but at extreme densities, quantum effects dominate. Loop quantum gravity predicts that these quantum effects create a repulsive force. Instead of matter crushing inward to a singularity, it bounces outward. The Big Bang becomes a big bounce. This is not speculation. It is a direct consequence of the mathematics. When physicists apply loop quantum gravity to cosmology, they find that the universe does not begin at a singularity. It transitions from a contracting phase to an expanding phase. The bounce is smooth and well-defined. What does the pre-bounce universe look like? According to the calculations, it looks a lot like ours. A classical space-time with stars, galaxies, and normal matter. But it is collapsing. Everything is falling inward. Galaxies approach each other. Space shrinks. Density increases. Then, at a critical point, the quantum bounce happens. The collapse reverses. Expansion begins. The universe before the bounce could have lasted billions of years. It could have had its own history of structure, formation, and evolution. But that history is mostly lost. The bounce creates what physicists call cosmic forgetfulness. The extreme quantum conditions during the transition scramble information. Only broad features survive. The fine details are erased. Think of compressing a photograph to a tiny file size. You lose resolution. You lose detail. What remains is a blurry outline. The bounce does something similar to the universe. It preserves overall properties like total energy and spatial geometry, but destroys specific information about stars, planets, or any complex structures. This is confirmed by computer simulations. When physicists model the bounce, they find that quantum fluctuations grow enormously during the transition. These fluctuations wash out classical information. By the time the universe expands again, almost no memory of the previous state remains, just a few parameters that set the initial conditions for the new expanding phase. Does this mean loop quantum gravity solves the before the Big Bang problem? Partially. It replaces the singularity with a bounce, which is progress. It shows that physics can extend through the transition, which is important, but it does not tell us where the collapsing universe came from. It pushes the question back one step. Was there a bounce before the bounce? An infinite series of bounces stretching into the past? Or was there a true beginning at some earlier time? Loop quantum gravity does not answer this. The equations describe the bounce, but they do not specify what came before the collapsing phase. Still, this is real progress. It shows that the singularity is not inevitable. Quantum gravity can smooth it out. The universe can pass through extreme conditions without breaking down, and that opens the door to understanding the ultimate origin. The mechanism behind the Big Bounce is quantum geometry. This is the core insight of loop quantum gravity. Space is not a backdrop where physics happens. Space itself is physical. It has structure. It has properties. And at high densities, those properties change. In normal circumstances, gravity pulls things together. Two masses attract. Space curves inward around them. This is Einstein's general relativity. It works perfectly for stars, galaxies, and even black holes, but it fails at the Planck density. That is about 10 to the 94 grams per cubic centimeter. For comparison, atomic nuclei have densities around 10 to the 14. The Planck density is 80 orders of magnitude higher. At this density, quantum effects of space become dominant. The discrete structure of space generates a repulsive force. It is not a new type of interaction. It is a consequence of geometry itself. When space is compressed beyond a certain point, it resists further compression. The quantum geometry pushes back. Picture a spring. Compress it, and it pushes back harder. Eventually, it reaches a point where you cannot compress it further. The resistance overcomes the applied force. Space behaves similarly at extreme densities. The quantum nature of geometry acts like a spring, preventing total collapse. This repulsion does not violate general relativity. It is a quantum correction to it. General relativity assumes space is continuous. Loop quantum gravity adds the next level of detail. Space is discrete. At normal densities, this makes no difference. But at extreme densities, it changes everything. The singularity is replaced by a bounce. The bounce happens fast. The universe passes through the maximum density in an incredibly short time, much shorter than a second. During this time, space is highly quantum. It does not behave like classical geometry. It is a roiling network of quantum loops. But before and after the bounce, space is classical, smooth, well described by general relativity. This creates two classical branches: the contracting universe before the bounce, the expanding universe after. They are connected by a quantum bridge. Information can pass through this bridge, but it is severely limited. Most details are lost. Only the coarsest features survive. Physicists have performed detailed simulations of this process. They evolve the quantum state through the bounce and measure what emerges. The results are consistent. The expanding universe has a specific set of initial conditions: low entropy, nearly uniform density, small quantum fluctuations, exactly what we observe in our universe. This is remarkable. Loop quantum gravity does not require fine-tuning to produce the right initial conditions. They emerge naturally from the bounce. The process automatically creates a universe, ready for structure formation, ready for galaxies and stars and planets, ready for life. But there is a catch. The simulations also show that not all pre-bounce universes lead to good post-bounce universes. If the contracting universe has certain properties, the bounce can fail. The quantum state becomes too chaotic. The expanding universe would be wildly inhomogeneous. It would not look like ours. This means the pre-bounce universe must have had certain features. It could not have been completely arbitrary. It needed to be relatively smooth and classical. But why? Where did that smooth contracting universe come from? Did it also emerge from a previous bounce? If so, we are back to an infinite regress. Some physicists argue that loop quantum cosmology only works for one bounce, a single cycle from contraction to expansion. Before the contracting phase, there was something else, maybe inflation, maybe a different state entirely. The bounce connects two epochs, but does not imply an eternal cycle. Others believe multiple bounces are possible. They suggest that each bounce slightly resets conditions. Over many cycles, the universe settles into a stable pattern. This would make the current epoch typical rather than special, but the mathematics here is unclear. More work is needed. What we can say with confidence is this: loop quantum gravity provides a concrete mechanism for avoiding the singularity. The Big Bounce is not a vague idea. It is a prediction that emerges from applying quantum mechanics to geometry, and it suggests that something existed before the Big Bang, a contracting universe that reached maximum density and rebounded. Loop quantum gravity predicts that before our expanding universe, there was a contracting one, not a mirror image, not exactly the same, but a classical cosmos that behaved according to the laws of general relativity. Stars shined, galaxies formed, space had geometry and structure. Then, everything began to fall inward. The collapse was gradual at first. Galaxies that were moving apart started moving together. The cosmic expansion reversed. This would happen if dark energy, the force accelerating our current expansion, somehow weakened or changed sign. Gravity would take over. The universe would begin contracting. At first, nothing seems unusual. Stars continue burning. Planets orbit normally. Life, if it existed, would notice nothing wrong. But over billions of years, galaxies get closer. The night sky brightens. More and more galaxies become visible as the space between them shrinks. Eventually, galaxies begin to merge. The cosmic microwave background, which in our universe comes from the distant past, would come from the distant future in the contracting phase. The universe ahead of you in time appears hot. The universe behind you appears cold. This inversion of thermodynamics is strange, but mathematically consistent. As contraction continues, the density increases. Gas between galaxies heats up. Stars collide more frequently. Black holes merge. The temperature everywhere rises. What was once cold intergalactic space becomes warm, then hot, then blindingly brilliant. The universe fills with radiation. At some point, atoms break apart. Electrons strip away from nuclei. Matter returns to the plasma state that existed shortly after our Big Bang. But this time, the process runs in reverse. The universe is not cooling and forming structure. It is heating and destroying structure. Eventually, even atomic nuclei disintegrate. Protons and neutrons dissolve into quarks and gluons. The universe becomes a quark soup. Density climbs higher and higher. General relativity predicts this should lead to a singularity, but loop quantum gravity says otherwise. Before the singularity can form, quantum effects take over. The quantum geometry of space resists the crush. As density approaches the Planck scale, about 10 to the 94 grams per cubic centimeter, the repulsive force activates. Space cannot compress further. The collapse stops, then reverses. The bounce occurs. The universe begins expanding again. This expanding phase is our universe. The Big Bang we observe is the moment of reversal, not a creation from nothing, but a rebound from maximum compression. The hot, dense state we call the early universe is the immediate aftermath of the bounce. Space expands, density drops, temperature falls, particles condense out of the quark soup, nuclei form, atoms form, stars ignite. But what happened to all the structure from the contracting phase? The galaxies, the stars, the potential civilizations, they were erased. The bounce is a destructive event. Anything complex gets torn apart by quantum fluctuations. The information scrambles. By the time the expanding phase begins, no trace remains of specific objects, no fossils, no ruins, no signals. Only statistical properties survive. The total energy, the spatial curvature, the distribution of quantum fluctuations. These set the initial conditions for our universe. They determine how quickly space expands, how dense matter is, how lumpy the distribution becomes. But they contain no memory of what the contracting universe actually looked like in detail. This is both disappointing and necessary. Disappointing because we cannot learn about that earlier epoch. Necessary because if too much information survived, our universe would be overdetermined. Its properties would be fixed by the previous cycle rather than by physical laws. The cosmic forgetfulness allows each cycle to be fresh, to evolve according to its own dynamics. Still, the basic picture is clear. Before our Big Bang, there was a cosmos. It had space, time, matter. It evolved, then it collapsed, and from that collapse, we emerged. The universe has amnesia. This is not metaphor. It is a mathematical result. When physicists calculate what information passes through the Big Bounce, they find that almost everything is lost. The transition erases the past. We can never know the full details of what came before. This cosmic forgetfulness happens because of quantum fluctuations. During the bounce, when density reaches the Planck scale, space behaves quantum mechanically. It stops being a smooth fabric. Instead, It becomes a churning network of quantum geometries. This environment is chaotic, turbulent. Anything trying to pass through gets scrambled. Think of signal transmission. Send a clear message through a noisy channel, and the message degrades. Add enough noise, and the message becomes unrecoverable. Only the most basic features survive. The bounce is like a channel with infinite noise. It destroys almost all information about the contracting phase. What survives? Only parameters that cannot be erased. The total energy of the universe, whether space is flat, curved inward, or curved outward. The spectrum of quantum fluctuations, but not their specific arrangement. These are coarse properties. They constrain the post-bounce universe, but do not specify its detailed configuration. Martin Bojewald, a physicist at Pennsylvania State University, proved this mathematically. He showed that the equations of loop quantum cosmology contain complementary parameters. Some are relevant only before the bounce, others are relevant only after. They do not determine each other. This means knowledge of the pre-bounce state does not give complete knowledge of the post-bounce state. Information is lost. This has profound implications. It means we can speculate about what existed before the bounce, but we cannot know for certain. We can construct models, we can make educated guesses, but we cannot extract definitive answers from observational data. The past is hidden behind an impenetrable barrier. Some physicists see this as a limitation. We want to know everything. We want the complete history of the cosmos. Cosmic forgetfulness denies us that. It draws a line beyond which our knowledge cannot reach. This feels frustrating, incomplete, but others see it differently. They argue that cosmic forgetfulness is necessary for science to work. If every detail of our universe were determined by an earlier cycle, then explaining our universe would require explaining that earlier cycle, and that one would require explaining a previous one. The chain never ends. You never arrive at a fundamental explanation. Cosmic forgetfulness cuts this chain. It means our universe can be understood largely on its own terms. Yes, it emerged from a pre-bounce state, but that state does not micromanage the present. It only sets broad initial conditions. Everything since the bounce follows from physical laws, not from arbitrary historical contingency. There is an analogy to human memory. You do not remember every detail of your life. You remember highlights, emotional moments, general patterns. The rest fades. This forgetting is not a bug. It is a feature. It prevents your mind from being overwhelmed by irrelevant data. Similarly, the universe forgets details, but remembers essentials. The extent of cosmic forgetfulness depends on how long the bounce lasts. A quick bounce erases more information than a slow one. Current calculations suggest the bounce is extremely brief, much less than a Planck time. This implies maximum erasure, almost total amnesia. But there is a catch. Some information might survive in unexpected ways. Patterns in the polarization of gravitational waves, subtle correlations in the distribution of galaxies, higher-order effects that current calculations miss. Future observations might find these hidden memories. They might crack the amnesia barrier and reveal glimpses of the pre-bounce cosmos. For now, the conclusion stands. We live in a universe with a past it cannot remember. The big bounce reset the clock. Whatever came before is lost, preserved only in the roughest outline. This is the price of avoiding the singularity. The universe passes through the crisis but forgets how it got there. Does this mean the question of what came before is unanswerable? Not exactly. We can still ask what kind of universe would lead to the initial conditions we observe. We can use physics to narrow the possibilities. We can test models against data, but we will never have certainty. The past will always be partially hidden. Cosmic forgetfulness guarantees that some mysteries remain forever beyond our reach. Inflation creates a problem, a beautiful, elegant, observationally confirmed problem. Once inflation starts, it might never completely stop. In most regions, it continues forever, creating new universes constantly, an infinite multiverse, bubbling out of eternal expansion. This is not speculation. It is a prediction of the simplest inflationary models. Here is how it works. Inflation ends when the inflaton field decays to a lower energy state. But this decay does not happen everywhere simultaneously. It happens randomly. Quantum fluctuations trigger the transition in some regions before others. When a region transitions, it becomes a bubble universe. Our observable cosmos is one such bubble. Outside the bubble, inflation continues. Space keeps doubling. Other bubbles form. Each one is a separate universe with its own hot Big Bang. These bubble universes are causally disconnected. No signal can travel between them. They are expanding away from each other faster than light can cross the gap. They exist in the same space, but they can never interact. This process never stops. As long as inflation continues somewhere, new bubbles keep forming, and inflation continues in most places. The rate at which space expands exceeds the rate at which bubbles form. The inflating region grows faster than it gets consumed by bubble formation. The multiverse is eternal and infinite. Alan Guth and Andre Linde developed this idea in the 1980s. They called it eternal inflation. At first, it seemed like an exotic possibility. Maybe inflation ends completely. Maybe the multiverse is finite. But as physicists studied the equations, they realized eternal inflation is generic. Almost any inflationary model leads to it. Avoiding eternal inflation requires fine-tuning. What does this mean for the before the Big Bang question? It means our hot Big Bang is not the beginning of everything. It is one event in an infinite sea of such events. The true beginning, if there is one, happened when inflation first started, when the inflaton field first began, driving exponential expansion. That moment is pushed infinitely far into the past, or eliminated entirely. Some versions of eternal inflation are past eternal. They have no beginning. Inflation has always existed. This sounds impossible. How can something always have existed with no starting point? But the mathematics allows it. In an eternally inflating space, you can follow any timeline back indefinitely. There is no first moment. Time extends infinitely into the past. Other versions have a beginning. Inflation started from some initial condition, maybe a quantum fluctuation, maybe a transition from a different phase. But even then, the beginning is pushed to a higher level. You are not asking when our universe began. You are asking when the multiverse began. And that question might have no answer, because the multiverse generates its own time. The multiverse creates interpretive challenges. If infinite universes exist, then anything that can happen does happen. Somewhere, in some bubble, there is a universe where you made different choices. A universe where Earth never formed. A universe where the laws of physics are slightly different. Every possibility is realized infinitely many times. This makes predictions difficult. How do you test a theory if it predicts everything? Some physicists argue you use anthropic reasoning. We can only observe universes where conditions allow observers to exist. This selects a subset of the multiverse. Our observations are biased toward life-friendly regions, but this explanation feels unsatisfying. It replaces sharp predictions with probabilistic selection effects. Others argue the multiverse is unscientific. If you cannot observe other universes, if you cannot test their existence, then they are metaphysics, not physics. The theory makes no falsifiable predictions. It explains everything and therefore explains nothing. This criticism has merit. Science relies on testability. Ideas beyond testing are philosophy, however mathematically beautiful. Yet eternal inflation is not added by hand. It emerges from the same equations that explain our observable universe. The theory that predicts the correct pattern of galaxies also predicts the multiverse. You cannot easily separate them. Accept inflation, and you likely get eternal inflation. Reject eternal inflation, and you need to explain why inflation stops everywhere at once, which requires fine-tuning. This is the multiverse problem. A successful theory leads to a conclusion that challenges the foundations of science. It suggests our universe is one of infinitely many, making our existence seem arbitrary. It turns the question of what came before the Big Bang into a question about the entire multiverse, and it might place that answer forever beyond reach. If the multiverse exists, each bubble universe could have different laws of physics, not wildly different. They all emerge from the same underlying theory, but different enough that electrons might have different masses, stars might burn differently, atoms might not form at all. This variation comes from the landscape of possible vacuums. In string theory, the 6 extra dimensions can curl up in many different ways. Each configuration produces different particle physics. The shape determines what particles exist, what their masses are, how strongly they interact. The number of possible shapes is enormous. Estimates range from 10 to the 500 to potentially infinite. Each shape corresponds to a different vacuum state. A vacuum in physics is not empty space. It is the lowest energy configuration of fields. Different vacuums have different properties. In our vacuum, electrons are light, protons are heavy, and gravity is weak. In another vacuum, these values could differ. The electron might be massive, the proton might be light, gravity might be strong. During inflation, different bubble universes can settle into different vacuums. As the inflaton field decays, it transitions to one of the many possible low-energy states. Which state it chooses is random. Quantum fluctuations determine the outcome. Some bubbles get our vacuum, others get different vacuums. The multiverse samples the entire landscape. This has a remarkable consequence. The properties of physics in our universe might not be fundamental. They might be environmental. Like the temperature of a planet, temperature varies from planet to planet, but the underlying laws of thermodynamics are universal. Similarly, particle masses and force strengths might vary from universe to universe, while the underlying string theory remains universal. This resolves some puzzles. Why is the electron mass what it is? Why is gravity so weak? Traditional physics has no answer. The values seem arbitrary. But in the multiverse picture, they are explained by selection. We observe these values because they allow complexity to form. Different values would produce sterile universes. No stars, no chemistry, no observers. This is anthropic reasoning. We are not typical. We exist in a rare bubble where conditions allow life. The vast majority of bubbles might be dead, too hot, too cold, wrong particle masses. But we cannot observe those. We only see the universe where we exist. Our observations are biased by our own existence. Some physicists hate this explanation. It feels like giving up. Instead of calculating why the electron has its mass, you say it could have any mass, and we happen to live where it has the right value. This is not a prediction. It is a postdiction, explaining the outcome after the fact rather than predicting it in advance. Others embrace it. They argue that not everything in physics needs to be calculable from first principles. Some things can be environmental accidents. Just as biology does not predict the exact shape of every tree from fundamental laws, physics might not predict every constant of nature. The framework is fundamental. The details are contingent. The debate is unresolved. It hinges on whether you think physics should explain everything or only the deepest principles. If every constant of nature must be derived from theory, then the landscape picture fails. It leaves too much unexplained. But if physics explains the framework and lets the details vary, then the landscape is acceptable. It is a new layer of reality, like discovering that Earth is one planet among many. Testing this is hard. We cannot visit other universes. We cannot measure their electron masses. But we can look for indirect evidence. Collisions between bubble universes would leave marks on the cosmic microwave background, specific patterns of hot and cold spots. Experiments have searched for these. So far, they found nothing. Either bubble collisions are rare, or our detection methods are not sensitive enough. Another test involves the distribution of constants in our universe. If the landscape picture is correct, we should find ourselves near the edge of the region where life is possible, not in the center. This is because regions near the boundary are more common. They occupy more volume in the space of possibilities. Preliminary studies suggest this might be true, but the evidence is weak. For now, the question remains open. Does physics vary across the multiverse? Or are the constants we measure truly fundamental, fixed by deeper principles we have not discovered? The answer would reshape our understanding of reality. It would tell us whether our universe is typical or special, whether the laws we discover are universal or local, whether science can explain everything or only the structure within which everything happens. In quantum mechanics, nothing is unstable. The vacuum seethes with activity. Particles pop in and out of existence. Fields oscillate. Energy appears and disappears. This is not theoretical. It is measured. The Casimir effect, where two metal plates attract in vacuum, is caused by virtual particles. Quantum fluctuations are real. Could the universe itself be a quantum fluctuation? Could it have appeared from nothing the way virtual particles do? This idea, championed by physicist Alexander Vilenkin, suggests that the universe tunneled into existence from a state with no space, no time, no matter. Just the laws of quantum mechanics operating in some abstract sense. The key word is tunneling. In quantum mechanics, particles can cross barriers they classically could not. An electron can tunnel through a wall, even though it lacks the energy to climb over. The probability is low, but not zero. Vilenkin proposes that the universe did something similar. It tunneled from nothing into something. Nothing here does not mean absolute nothingness. It means a state with minimal properties, no classical spacetime, no particles. But quantum fields still exist in a potential form. The laws of physics are still operating. This is the quantum vacuum at its most fundamental level, the starting point from which everything else emerges. How does this work mathematically? Vilenkin uses a concept called Euclidean time. In normal time, events are ordered: past, present, future. But in Euclidean time, this ordering dissolves. Time becomes space-like. The universe can be described as a four-dimensional shape with no boundary, no beginning, no moment of creation. As you follow this shape forward in Euclidean time, it transitions to normal time. The imaginary time axis rotates into the real time axis. Space emerges. The universe begins expanding. From our perspective, inside the universe, this looks like a sudden beginning, a big bang. But from the outside, in the Euclidean description, there is no beginning. The universe simply exists as a geometric object. This idea is related to Hawking's no-boundary proposal, but with a key difference. Hawking suggested the transition happens near the Big Bang. Vilenkin suggests it happens before. The tunneling creates a small universe in an inflationary state. That universe then expands exponentially, eventually transitioning to the hot Big Bang. Our universe is the result of a quantum fluctuation that tunneled from nothing into inflation. The probability of this tunneling is extraordinarily low, but in quantum mechanics, anything with non-zero probability happens eventually. Given infinite time or infinite opportunities, even the most unlikely events occur. The universe might be one such unlikely event, a statistical fluke allowed by quantum mechanics. Critics point out problems. Quantum mechanics requires time to operate. You need a before and after for probabilities to make sense. But if time itself is created by the tunneling, what does it mean to say the tunneling has a probability? You cannot use time-dependent quantum mechanics to describe the creation of time. Vilenkin responds that quantum mechanics can be formulated without explicit time. You use the Wheeler-DeWitt equation, which describes quantum states of the universe without reference to external time. In this framework, probabilities are assigned to different geometries rather than to different moments. The tunneling is a transition between geometric states, not between temporal states. Whether this resolves the problem is debatable. Some physicists find it convincing. Others remain skeptical. The debate touches on deep issues in quantum gravity. How do you describe a system when time itself is part of the system? What does probability mean when there is no external clock? Despite these challenges, The tunneling from nothing picture has influenced cosmology. It provides a framework for discussing the origin of the universe without invoking a singularity. It connects the Big Bang to fundamental quantum processes, and it suggests that the universe is not a miracle or a mystery, but a natural consequence of quantum mechanics applied to gravity. But there is another quantum puzzle. The vacuum itself has energy, and that energy has bizarre properties. Empty space weighs something. This is one of the strangest facts in physics. Even when you remove all particles, all radiation, all fields, the vacuum itself has energy. This vacuum energy exerts pressure. It affects the expansion of the universe. We call it dark energy today, and it makes up about 68% of everything that exists. But here is the paradox. When you calculate how much vacuum energy there should be, using quantum field theory, you get an absurd answer. The calculation gives a value that is 10 to the 120 times larger than what we observe. This is the worst prediction in the history of physics, off by 120 orders of magnitude. Why is the calculation so wrong? We do not know. Every quantum field contributes to the vacuum energy. Electrons, quarks, photons, all of them have quantum fluctuations, even in their lowest energy state. Sum up all these contributions, and you get an enormous number. But the observed vacuum energy is tiny, almost zero. Something cancels almost all of it. But what? Some physicists proposed supersymmetry. This theory predicts that every particle has a superpartner with opposite statistical properties. Fermions have boson partners. Bosons have fermion partners. The contributions of partners cancel. The vacuum energy drops to zero, or nearly zero. This would solve the problem. But experiments at the Large Hadron Collider found no evidence for supersymmetry, at least not at accessible energies. If supersymmetric particles exist, they are heavier than we can currently produce. This makes the cancellation mechanism less attractive. It requires higher energy partners, which means less precise cancellation. The problem remains. Another idea involves the landscape of string theory. Maybe the vacuum energy can take many different values depending on which vacuum you are in. Most values are large, but some are small. We live in a universe with small vacuum energy because only such universes allow structure to form. Large vacuum energy would prevent galaxies from forming. This is anthropic reasoning again. The value is what it is, because otherwise we would not be here to measure it. This explanation is controversial. It does not calculate the vacuum energy. It selects it from a range of possibilities. Many physicists find this unsatisfying. They want a theory that predicts the value, not one that says it could be anything. Yet the vacuum energy is real. We measure its effects. The universe is accelerating. Galaxies are moving apart faster over time. This acceleration requires something to push space apart. That something is vacuum energy. It acts like a cosmological constant, a term Einstein introduced, then abandoned, then turned out to be correct after all. During inflation, vacuum energy was huge, much larger than today. It dominated everything. Its pressure drove the exponential expansion. Then it decayed, converting into particles and radiation. Most of it disappeared, but a tiny remnant remained. That remnant is what we call dark energy now. Why did a remnant remain? Why did the vacuum energy not go completely to zero? This is the cosmological constant problem. We have no good answer. The observed value is small, but not zero. It is roughly 1 particle per cubic meter. This seems random. There is no natural scale in physics that explains this number. Some physicists think the solution requires new physics. Maybe gravity is modified at very large scales. Maybe dark energy is not vacuum energy, but a new field. Maybe our calculations are wrong because we misunderstand quantum field theory in curved spacetime. These are active areas of research. No consensus has emerged. What does this have to do with what came before the Big Bang? Everything. Vacuum energy drives inflation. It creates the pre-Big Bang state. If we do not understand vacuum energy, we do not fully understand inflation. The origin of our universe is tied to this unsolved puzzle. Cracking the vacuum energy paradox might reveal where inflation came from, why it started, whether it is eternal or had a beginning. For now, we live with the mystery. Empty space has energy. That energy is much smaller than theory predicts, and that energy might have been responsible for creating the universe as we know it. Understanding what happened before the Big Bang requires solving Einstein's equations in conditions so extreme that analytical methods fail. The math becomes impossible. Infinities appear. Approximations break down. The only way forward is brute force computation. This is numerical relativity, using supercomputers to simulate gravity under extreme conditions. The challenge is immense. Einstein's equations are 10 coupled, nonlinear partial differential equations. In simple situations, you can solve them with pencil and paper. But when spacetime is highly curved, when quantum effects matter, when nothing is symmetric or simple, you need computers, big computers, running for weeks or months, crunching numbers until a solution emerges. Physicists Eugene Lim, Katie Clough, and Josu Orikoexia published a paper in 2025 outlining how numerical relativity could explore pre-Big Bang physics. They argue that inflation and what came before cannot be understood without computational methods. The equations are too complex, the conditions too extreme. We need simulations. Here is what they propose. Start with some initial state before inflation. Do not assume the universe was smooth or symmetric. Allow it to be lumpy, chaotic. Then evolve it forward in time using the full Einstein equations plus quantum corrections. See what happens. Does it inflate? Does it collapse? Does it do something unexpected? This approach is radical because it does not presuppose the answer. Most cosmological models assume homogeneity. They assume the universe is the same everywhere. This simplifies the math enormously, but it might be wrong. The pre-inflationary universe might have been wildly inhomogeneous. Numerical relativity can handle that. It makes no symmetry assumptions. The simulations could test scenarios that are otherwise inaccessible. Ekpyrotic Brane collisions, big bounces with complex pre-bounce states, cyclic cosmologies, multiverse collisions. Each scenario has equations. Run the simulation. Compare the output to observations. Some ideas will survive, others will fail. This is how science progresses when theory alone is insufficient. But there are obstacles. The biggest is computational cost. Simulating the full quantum gravity equations for cosmology requires resources that barely exist. Current supercomputers struggle. Future ones might succeed. Progress is being made. Better algorithms, more efficient code, faster machines. Within a decade, some of these simulations might become feasible. Another obstacle is knowing what to simulate. You need initial conditions, but we do not know what the pre-Big Bang state was like. You can make educated guesses. You can try different scenarios. But the space of possibilities is vast. Computational power is limited. You cannot simulate everything. You must choose wisely. Despite these challenges, numerical relativity has already achieved remarkable success in other areas. Simulations of colliding black holes predicted gravitational wave signals that were later detected by LIGO. The match between simulation and observation was stunning. This proves the method works. It can handle strong gravity. It can make testable predictions. Applying the same approach to cosmology is natural. Black holes and the Big Bang both involve extreme curvature. Both push general relativity to its limits. If numerical relativity cracked the black hole problem, it might crack the Big Bang problem too. The techniques are similar. The physics is related. Researchers are also developing methods to include quantum effects in simulations. This is harder. Quantum field theory on curved backgrounds is notoriously difficult, but progress is being made. Effective field theory methods allow approximate treatment of quantum corrections. Loop quantum gravity provides a framework for discrete spacetime. String theory offers its own computational techniques. Combining these approaches might give us a window into the pre-Big Bang universe. Not a perfect view, not complete understanding, but glimpses, hints, patterns that match or contradict observations. This would be progress, real progress, moving from pure speculation to testable models. The hope is that within the next 10 to 20 years, simulations will constrain what happened before the Big Bang. They will rule out some theories, support others, narrow the range of possibilities. This will not give us a final answer, but it will advance the frontier, push our knowledge deeper into the mystery of origins. To test what came before the Big Bang, we need to observe signals from that era. These signals exist. They are imprinted on the cosmos we see today, but detecting them requires instruments at the edge of current technology, and in some cases, beyond that edge. Here is what we are looking for. First, primordial gravitational waves. These are ripples in space-time generated during inflation. As space expanded exponentially, quantum fluctuations in the gravitational field got amplified. They became real gravitational waves with wavelengths spanning the observable universe. These waves have been traveling through space ever since, carrying information about the inflationary epoch. Gravitational waves affect the polarization of the cosmic microwave background. They create a specific pattern called B modes. This pattern is distinct from the E modes caused by density fluctuations. Detecting B modes would confirm inflation. More importantly, measuring their strength would tell us how energetic inflation was, how high the energy density reached. This constrains models of the pre-Big Bang state. Several experiments are searching for B modes. The Bicep and Keck telescopes in Antarctica, the Planck satellite, future missions like Lightbird and CMBS-4. These instruments measure polarization with exquisite precision. They map the entire sky. They filter out foreground contamination. The goal is to find the primordial signal buried in the noise. So far, no confirmed detection. Upper limits keep improving. The signal, if it exists, must be weaker than initial estimates. This tells us something. It suggests inflation happened at lower energy than some models predict. It rules out the simplest, most energetic inflationary scenarios. The surviving models involve more complex dynamics, more subtle physics. Second, we look for deviations from perfect scale invariance. Inflation predicts that quantum fluctuations have roughly the same amplitude at all scales. Roughly, but not exactly. The small deviations carry information. They tell us how the inflaton field evolved, whether it accelerated or decelerated, whether there were multiple fields or just one. Precision measurements of the cosmic microwave background reveal these deviations. The Planck satellite measured the temperature variations to incredible accuracy. The data matches inflationary predictions beautifully. But there are hints of anomalies, a slight asymmetry between hemispheres, a deficit of power at large angular scales. These might be noise, or they might be real signals from the pre-Big Bang physics. Third, we search for non-Gaussianity. Gaussian fluctuations are random and uncorrelated. Non-Gaussian fluctuations have patterns, correlations, higher order structure. Different pre-Big Bang scenarios produce different non-Gaussian signatures. Inflation typically produces weak non-Gaussianity. Ekpyrotic models produce stronger signals. Bounce cosmologies produce different patterns still. Measuring non-Gaussianity requires analyzing billions of data points, looking for 3-point correlations, 4-point correlations, higher order statistics. The computational challenge is enormous, but it is doable. Current surveys like the Euclid satellite and the Vera Rubin Observatory will map billions of galaxies. Their distribution encodes information about primordial fluctuations, including non-Gaussianity. Fourth, we observe the large-scale structure of the universe, the distribution of galaxies, the shapes of galaxy clusters, the cosmic web of matter. All of this structure grew from tiny seeds planted during inflation. By mapping structure across cosmic time, we reconstruct how those seeds evolved. This tests our understanding of the initial conditions, which came from the pre-Big Bang state. Fifth, we look for exotic signatures, cosmic strings, domain walls, topological defects. These are predicted by some pre-Big Bang models, but not others. Finding them would rule out inflation in its simplest form. Their absence constrains what kind of phase transitions occurred, what symmetries broke, what fields were active. Sixth, we use gravitational wave detectors. LIGO, Virgo, CAGRA detect waves from black hole mergers. Future detectors, like LISA, the Einstein telescope, and Cosmic Explorer, will see waves from earlier epochs, potentially from phase transitions in the early universe. These transitions might have happened during or before inflation. The gravitational wave background would carry their signature. Testing requires patience. These observations take years, decades. Building the instruments, collecting data, analyzing it carefully, eliminating systematic errors. The payoff is understanding. Each measurement constrains theories, narrows possibilities, brings us closer to knowing what happened before the Big Bang. There are boundaries to what we can observe, hard limits imposed by physics itself. No matter how advanced our instruments become, some information is forever hidden. Understanding these limits is crucial. It tells us what questions are answerable and what questions are not. The most fundamental limit is the cosmic horizon. Light travels at a finite speed. Since the universe has a finite age, we can only see objects within a certain distance. This distance defines our observable universe, about 93 billion light-years in radius. Beyond that, light has not had time to reach us. We cannot see it. We never will. This horizon cuts off information. Whatever exists beyond it is inaccessible. If the universe is infinitely large, we only observe an infinitesimal fraction. If eternal inflation is correct, there are infinite bubble universes beyond our horizon. We cannot communicate with them. We cannot measure them. They might as well not exist from our perspective. Even within the observable universe, information is limited. The cosmic microwave background is our earliest direct observation. It comes from 380,000 years after the Big Bang. Before that, the universe was opaque. Photons scattered constantly. No light traveled freely. We cannot see earlier using electromagnetic radiation. The photon barrier is absolute. Gravitational waves penetrate further. They were not scattered by matter. In principle, they carry information from much earlier times, perhaps from the inflationary epoch itself. But detecting them is extraordinarily difficult. The signal is weak. The frequencies are hard to access. We need detectors we have not built yet, maybe cannot build. Neutrinos provide another window. They barely interact with matter. Neutrinos from the first second after the Big Bang should still be traveling through space. The cosmic neutrino background exists, but it has never been detected. The neutrinos are too low energy. They pass through detectors without leaving a trace. Detecting them might be impossible with any realistic technology. Then there is the information problem of the bounce itself. If loop quantum cosmology is correct, the big bounce erases details. Cosmic forgetfulness is built into the equations. No clever observation can circumvent it. The information is destroyed at the quantum level. It does not exist anymore. No signal carries it forward. This is a limit not of technology, but of physics. Inflation creates a similar problem. The exponential expansion smooths out primordial structure. Anything existing before inflation gets stretched beyond observability. Only quantum fluctuations from the end of inflation survive. Everything earlier is erased, pushed outside our horizon, diluted to undetectable levels. We cannot reconstruct the pre-inflationary state from post-inflationary observations. The multiverse, if real, might be forever beyond testing. If bubble universes are causally disconnected, we cannot observe them. No signal crosses the gap. The theory makes no observable predictions about those other universes. We can only observe our own bubble. This makes the multiverse hypothesis unfalsifiable in the traditional sense. Some argue this disqualifies it as science. Yet there are indirect tests. If bubble universes collided with ours, they would leave marks. A bruise on the cosmic microwave background, an asymmetry, a region with anomalous properties. Experiments have searched, found nothing. Either collisions are rare, or they leave signatures too subtle to detect, or the multiverse does not exist. We cannot tell which. Philosophical questions about the beginning might also be beyond observation. Why do the laws of physics have the form they do? Why does something exist rather than nothing? These are not questions observations can answer. They are metaphysical, outside the domain of empirical science. We can describe how the universe evolved, but why it exists at all might not be a scientific question. This does not mean we should stop asking, but it means we should be honest about the limits. Some questions we will answer, others we will narrow down. Still others will remain mysteries, not because we lack ingenuity, but because reality imposes boundaries on knowledge. The universe is under no obligation to make itself fully understandable to us. We are fortunate that so much is accessible, that the laws are comprehensible, that observations are possible at all. But there are edges to the knowable. Respecting those edges is part of intellectual humility. Still, the boundary keeps moving. What seemed impossible yesterday becomes routine tomorrow. The cosmic microwave background was theoretical speculation in the 1940s. By the 21st century, we map it in exquisite detail. Gravitational waves were fantasy in the 1960s. Now we detect them weekly. The impossible becomes possible. The limit advances. Maybe someday we will observe the Big Bounce, detect primordial gravitational waves from inflation, find evidence of the multiverse. Or maybe we will hit a wall, a true limit, an asymptotic boundary beyond which no progress is possible. Either way, the journey is worthwhile, because every step forward reveals something profound about reality. If the universe did not begin with the Big Bang, what does that mean for deeper questions? Questions about purpose, creation, meaning? These are not scientific questions, but they are human questions, and the science of what came before affects how we think about them. Traditional theology often points to the Big Bang as evidence of creation. The universe had a beginning, therefore it had a creator. Something outside the universe brought it into existence. This is the cosmological argument, refined and updated for modern cosmology. But if the Big Bang was not the beginning, this argument weakens. If inflation came before, if a bouncing universe preceded ours, if eternal inflation has no starting point, then the concept of a beginning dissolves. The universe becomes eternal in some sense. Not unchanging. It evolves. It goes through phases. But there is no first moment, no point where everything started from nothing. Does this eliminate the need for a creator? Not necessarily. One can argue that an eternal universe still requires explanation. Why these laws? Why this structure? Why something rather than nothing? The cosmological argument shifts from temporal origins to ontological dependence. The universe depends on something beyond itself for its existence, even if it has no beginning in time. Others argue the opposite. An eternal universe needs no external cause. It simply is. It has always existed in some form. Asking why is like asking why 2 + 2 = 4. There is no deeper reason. It is a brute fact. This view embraces the universe as self-sufficient, complete, not contingent on anything outside itself. Buddhism and some Eastern philosophies find this congenial. The concept of cyclic time, of endless universes arising and dissolving, appears in ancient texts. Conformal cyclic cosmology and bouncing models echo these ideas. Perhaps those philosophers intuited something about reality that science is now confirming, or perhaps it is coincidence. Humans have imagined many cosmologies. Some will match reality by chance. There is also the question of meaning. If the universe is one bubble in an infinite multiverse, does that make us insignificant? Are we cosmically irrelevant? just a statistical fluctuation in an endless sea of possibilities. Some find this disturbing. They want humanity to matter, to be central, to be special, but others embrace it. Insignificance can be liberating. It frees us from cosmic burden. We are not the point of creation. The universe does not exist for us. We are free to create our own meaning, to define our own purpose, without needing cosmic validation. This is the existentialist response to cosmology. Science itself remains neutral. It describes what is, not what should be. Physics tells us how the universe evolves. It does not tell us how to live. That is a separate question, requiring separate tools: ethics, philosophy, personal reflection. Science informs the conversation but does not dictate conclusions. What science does provide is perspective. We thought the universe was 6,000 years old. It is billions. We thought Earth was the center. It is not. We thought the Milky Way was the whole cosmos. Galaxies beyond number exist. We thought the Big Bang was the beginning. It might not be. Each discovery humbles us, expands our view, challenges assumptions. This process can be uncomfortable. It disrupts narratives, questions authority, forces rethinking, but it is also exhilarating. We live in a universe richer and stranger than our ancestors imagined. The boundaries of reality extend further than we thought possible. What came before the Big Bang is not just a physics question. It is a question about the nature of existence itself. If we find the answer, it will reshape philosophy, theology, our understanding of our place in the cosmos. If we do not find the answer, that too tells us something about the limits of knowledge, about the mystery at the heart of things. Either way, asking the question transforms us, because the question forces us to confront the deepest puzzles of existence. Why is there something rather than nothing? We do not know. Maybe science will answer it, maybe not. But the fact that we can ask, that we can investigate, that we can push the boundaries of understanding, that itself is remarkable. We are the universe trying to understand itself, and that quest, regardless of where it leads, is profoundly meaningful. The next 50 years will transform our understanding of cosmic origins. New instruments are coming online. Experiments are planned. Technology advances. What seemed impossible is becoming feasible. Here is what we might discover about what came before the Big Bang. Gravitational wave astronomy is entering its golden age. Current detectors see black hole mergers. Next generation detectors will see much more. The Einstein telescope, Cosmic Explorer, LISA, in space. These will detect gravitational waves from the early universe, from phase transitions, from cosmic strings, potentially from inflation itself. If the signal exists, we will find it. A detection would revolutionize cosmology. It would confirm inflation directly. It would measure the energy scale of the pre-Big Bang state. It would distinguish between competing models: inflation versus ekpyrotic, single field versus multiple fields, simple versus complex dynamics. The pattern of gravitational waves encodes this information. We just need sensitive enough detectors. Cosmic microwave background experiments are also advancing. Ground-based telescopes like the Simons Observatory and CMB S4 will map polarization across the full sky. Space missions like LightBird will follow. Each improvement in sensitivity brings us closer to detecting B modes, to measuring the primordial gravitational wave background, to seeing the fingerprint of the pre-Big Bang universe. Particle accelerators might contribute. The Large Hadron Collider continues searching for new physics. Future colliders, if built, would reach higher energies. They might discover particles or forces relevant to the early universe, supersymmetry, extra dimensions, new fields. These discoveries would constrain cosmological models, connect particle physics to the Big Bang. Astronomical surveys map the universe in unprecedented detail. The Vera Rubin Observatory will photograph billions of galaxies. The Euclid satellite will measure their shapes and positions. The Square Kilometre Array will map hydrogen across cosmic time. These surveys test inflation by measuring the primordial fluctuation spectrum, non-Gaussianity, scale dependence. Every measurement refines our understanding. Theoretical progress will continue. Loop quantum gravity is maturing. String theory is advancing. Numerical relativity is becoming feasible. New ideas emerge constantly. Some will fail. Some will succeed. The landscape of possibilities will narrow. We will identify which scenarios match observations and which do not. Artificial intelligence might accelerate discovery. Machine learning algorithms analyze data faster than humans. They find patterns we miss. They simulate physics efficiently. AI is already used in gravitational wave detection, in analyzing cosmic microwave background maps, in searching for anomalies. As AI improves, it will become a standard tool in cosmology. Quantum computing could also help. Simulating quantum gravity requires enormous computational power. Classical computers struggle. Quantum computers might excel. They naturally handle quantum systems. Once they scale up, they could simulate the big bounce, model quantum tunneling from nothing, explore the multiverse landscape. This is speculative, but plausible. Private space companies are changing the game. Cheaper launches, more satellites, better instruments. SpaceX, Blue Origin, and others make space access routine. This enables experiments that were previously too expensive. Small satellites, constellations of detectors, new kinds of telescopes. The pace of discovery accelerates. International collaboration grows stronger. The Event Horizon Telescope showed what coordinated global efforts achieve. Future projects will be even more ambitious, combining data from telescopes worldwide, coordinating observations across wavelengths, sharing resources and expertise. The questions are too big for any one nation. Collaboration is essential. Within decades, we might have answers, not complete answers. Science never offers those, but substantial progress. We will know whether inflation is confirmed beyond doubt, whether primordial gravitational waves exist, whether the universe bounced or tunneled or emerged from a multiverse collision. The pre-Big Bang state will shift from speculation to established science. Or we might find something unexpected, a signature no theory predicted, an anomaly that breaks our models. This would be even more exciting. It would mean reality is stranger than we imagined, that our theories, clever as they are, miss something fundamental. Discovery is not always finding what you expect. Sometimes it is finding what you did not. Either way, the future is bright. The questions are profound. The tools are improving. The community is engaged. We are living through a golden age of cosmology. The age when humanity learned what came before the Big Bang, when we pushed our understanding to the very edge of existence, when we discovered how the universe truly began. The journey continues. The mystery deepens and clarifies at the same time. Each answer spawns new questions. Each discovery reveals new puzzles. This is the nature of science, an endless frontier, always advancing, never complete. And that is exactly as it should be, because the universe is vast and strange and beautiful, and understanding it is the grandest adventure our species has undertaken.